right, and it is time for the last talk of the conference. So we have Amaury Hayat from the École des Ponts, which will be talking about guessing solutions of mathematical problems with transformers.
So thank you very much, Aurélien. Thank you very much for the invitation. So as you probably guessed from the title, my presentation is a follow-up from the presentation of François. So this means that if for any reason you haven't followed what François was saying, now is your second chance. So as a mathematician, this talk is very particular for me because not only it's the first time that I'm giving this talk, but it's also the first time that I'm not here to present a theorem, but rather some experimental results. And it's also the first time that I find myself in the situation of wondering, what do I say when I have only 3 papers in the field and I have already 3 co-authors who spoke at this conference? So lots of first times today. So, well, after all the talks of today and yesterday, I think the bar has been set very high, so it's a bit intimidating. And I didn't know how to start, so I decided that I should start by a story. And this story started at the beginning of 2018. So I was having lunch at Facebook, at the time it was called Facebook still, with Alexis Conneau and Guillaume Lample. And I realized during the lunch that I wasn't the only one daydreaming about one day using AI and math. So we talked about it with Guillaume, and we thought, okay, that sounds to be something super cool. Maybe let's just finish our PhDs first and even try to secure a position if we can, and then let's do this. So yeah, just, you know, in every good story you have a context, and now the context is the beginning of 2018. I guess it's about the time where Kevin Buzzard and Patrick Massot decided to formalize the definition of perfectoid spaces, at least if I followed the talk of this morning accurately. So August 2018, it's the International Congress of Mathematicians. So for those who don't know these events, this is something that happens once every 4 years. It's really the biggest math event on the planet. It's where the Fields Medal are awarded. And when you're there, you're hearing to the plenary speakers who are like Oscarized mathematicians. And one of them, in the introduction, said, really, you should look at what AI is doing in languages, because it's amazing. So really, there was the idea that there is something to do there. And then the story takes a turn on October 16th, 2019, the day before Guillaume Lample's defense, where I receive a message from Guillaume saying, will you be able to come tomorrow? There's something I'd like to talk to you about. And that was the paper that François showed, Deep Learning for Symbolic Mathematics. So we started working together, and in 2020, we submitted an article, Learning Advanced Computation by Examples. And this is what I'm going to talk about. So in the next, say, 30, 40 minutes, if I'm managed to make this timing, I'd like to show you a few classical problems. So some of them are known. They have a very well-made and defined solution and theorems that you can apply, and we know how to solve them. Others, we don't have a very satisfying way of solving them from a math point of view. And they are all problems that either you will know if you're a mathematician, or you will easily understand if you did some math in undergrad. So this is what I'm going to try to talk about. I'm going to show you what we're doing as mathematicians with those problems and what we can expect from an AI. So yeah, this is joint work with François Charton and Guillaume Lample. So let's see the 3 first problems. So the first problem is the stability problem. So you have a system of differential equations. Dot x is equal to f of x. I'm saying it's a system because x is a vector here. You have f of 0 is equal to 0. It means 0 is in equilibrium. You know, if you're at 0, x dot is equal to 0. And the question, it's a pretty simple question, is do all solutions tend to 0 when t goes to infinity? All right? So you have this system and you're wondering, can I show or do I know that all solutions tend to 0 when t goes to infinity? So this question, you've all seen this question before. If you think of a pendulum, if you have a pendulum and you just move the pendulum from its equilibrium position, then you all know that after some time, because there is some friction, the pendulum will go back to 0. So the answer will be yes for this system. Now you could think of other systems, like for instance, if you look at a satellite on a low orbit, Well, and if you think that 0 is the position of Earth, well, this is also a stable system. The solution will converge to 0. So because you are in a low orbit, there's still a bit of friction, and the satellite, if you don't do anything, will end up crashing on Earth. So this is after a very long time, but that's fine. We say t goes to infinity, so very long time is fine for us. And also, you could think of another type of problem, for instance, the famous three-body problem, where you know that this is a system where the answer is clearly no. So if you're in this room, it's because you probably believe, like me, that math don't need any application to be interesting. Math is interesting by itself, or by themselves. But it turns out that this problem does have a lot of applications if you're interested in this. So let's go back to our question. It's nice in the pictures, but that's our question. So do all solutions tend to 0 when t goes to infinity? So this is in fact a simple question, but a hard problem. We have no satisfying way of solving this from a math point of view. So we need somehow to simplify this question so that I can say something about it. And the way we'll simplify it is by saying, okay, provided the initial condition is sufficiently close to 0. So now you're not asking to know if all solutions tend to 0. You're just saying, if I'm starting close enough from 0, can I make sure that I will end up at 0 anyway, when t goes to infinity? And then in this case, it's simpler because you can look at the linear system. So when you're a mathematician or a master student or in some universities an undergrad, you can look at the linear system. So linear system is this system where A is a matrix. The matrix is the differential of f of your dynamics with respect to x at your equilibrium at 0. And in at least two simple cases, you have a theorem that tells you that you can find an answer if you look at the largest real part of the eigenvalues of your matrix. If this is a negative number, the answer is yes, and lambda is in this case, so, or rather so it should be minus lambda. So in this case, lambda, the absolute value of lambda is the speed of decay. And if lambda is positive, then the system is unstable, and now the absolute value of lambda is the speed of growth. Right, and I on purpose eliminate the case lambda is equal to 0, because in this case the question becomes very hard again, and we need to have a question that could be solved by a master student. So we'll go with this. All right, so this sounds like a very nice first task for a model. So we're going to use a transformer to try to guess the solution to this problem and try to see whether the transformer makes it or not. And the hope here, so yeah, I can give an example. For instance, you have the system on the left, and you'd like to guess, then the answer is yes. All right, so you can try to compute it. Hopefully I didn't make a mistake and the answer is indeed yes. If I did a mistake, you can tell me, feel free. And then the second question you can ask with this is, can you guess also the speed of decay or growth? And here lambda is minus 0.5, so well, you would like it to guess minus 0.5, or at least 0.5 if you just want the absolute value. All right, so what's the hope? The hope is that the transformer with no built-in mathematics, if you give it a lot of examples, so you give systems like the one on the left-hand side, answers just like on the right-hand side, and you give pairs like this, a lot of them, and maybe at the end of the day, the transformer who doesn't know anything, like not even 2 plus 2 is equal to 4, at the end of the day is still able to learn the theorem that's behind. So to answer not only on the examples you've provided, but on the whole space somehow. So you're trying to teach the theorem to a transformer and see whether it can work or not. All right, so now how do you do this? Well, we'll use a very classical transformer, just like the type of transformers that François was talking about, so relatively small, very far from the large language model that were mentioned in the talks of yesterday and today. And the generation procedure is relatively easy. You generate equations at random. So basically, you sample a tree at random, and then you fill it with operators or variables or integers, or even floats if you allow floats. So you fill the nodes, and then you have an equation at random. You generate several. So now you have a system generated at random, just like most of the systems I will just write in this presentation. You know that you have a math theorem. So given this system, you have a math theorem that is going to tell you the solution you're looking for. So you apply your theorem, you get the solution, and this is your training data set. Now, Now, this is a math object, so you just need to move from this to something that the transformer can ingest. So you will convert it as in a sequence of tokens, just like François was showing, and then you will feed it to the transformer, and at the end of the day, you hope that's going to work. A small remark of the number of examples we used, the order of magnitude is 10 millions. This could seem like a huge number, but if you think of all the possible functions you can possibly generate, so from a math point of view, then it's infinite and a lot of infinite because it's a vector space with an infinite dimension, so it's very large. But even if you look at the generator we built that has, of course, some finite parts, the number of examples you can generate is much, much higher than the number of atoms in the universe. So really 10 millions is a very tiny part. It's not like even the stars in the sky. It's even less than that. And the best proof is that if you try I mean, when we generated in total, a total of more than 100 millions, and we never got even a single duplicate, which is normal. I mean, the probability of having a duplicate is super low. So really, you're just looking at a few examples somewhere in your whole space, but it's a very, very sparse examples. All right, so if we look at the results on this first task. Yep. Yeah. So in fact, we're even restricting to oh yeah. So you're wondering if we extract we make sure there's no poles and yeah. So yeah, we do. We have a filter that so we're yeah. We're throwing away the things that are on C1 indeed. Otherwise, we have some troubles. So we can look at the results on this first task, and you can see that overall predicting the stability is pretty well, that works pretty well, like at 95%. It shouldn't be that much of a surprise because it has to do with the eigenvalues, and François was showing that you can predict the eigenvalues at 99%.
The eigenvalue, the matrix involves doing calculus.
Sorry? Yeah.
To differentiate your function.
Yeah, that's the point. So we don't give the linear system. So at some point, it's less obvious. That's why we're not at 99. It's because you're giving the nonlinear system, and at some point, it's not directly linked. So you need to do something. And chance level, of course, is 50 because we choose a data set. We're a balanced data set to make sure that the chance will be 50. So now you can see what happens now if I try to predict the speed of decay or growth. In this case, you get lower accuracy, but still quite high accuracy, given that you are trying to predict a number this time. So there is no chance level. I mean, chance level is nearly nothing. So you can try to see what happens with the number of equations. So 2, 3, 4, 5 are the number of equations here. So you can try to see what happens if you ask for a 10% tolerance or exact 2 digits, exact 3 digits, exact 4 digits. And you see that even for exact 4 digits, which is pretty precise for something like a transformer who's supposed to be an approximation, you get an accuracy that is not negligible at all. So that was our first experiment. What's interesting, and that's pointing to the question of Kevin here, is that if you are asking the transformer to give the linear system, so you train it to give the linear system, so you give it an information, you're basically adding a sub-question, saying compute the linear system and then find the answer. It doesn't change the accuracy, so it doesn't seem to help, even though for us, humans, I mean, that will be a very interesting sub-questions because really it will put you on the right path. All right, so let's complexify a little our system. So now we still have a system of differential equations, just like before, x dot is equal to f of x, but now you have an additional parameter u of t, and this u of t, it's also a vector, maybe a different dimension, and this u of t, you can choose it. It's a function you can choose. It's what we call a control. And the question is, how well can I control my system? What can I do with this? If I can choose u, what can I make the solution do, right? Where can I bring the solution with such a control? And if you ask it in a more mathematical way, with more mathematical words, it's a problem called controllability problem. And it's saying if you give t strictly larger than 0, an initial condition x1, a final point x0, can you make sure that I can find a u such that if I start at the initial point, I end up at the desired endpoint, right? So basically, the moral of the story is, can I make anything I want with this system by choosing u? And this is, again, a hard problem, but you can convert it as a problem for master students if you look at the local controllability. And now you just make sure that x0 and x1, so the initial condition and the point you want to reach, that are close enough to your equilibrium, to 0. And this is a typical problem you will find in the Master of Mathematics in Analysis. At some point, you might find this exercise. And you have a theorem, so Kalman's theorem, so it's not exactly Kalman, it's the nonlinear extension of Kalman's theorem, that tells you that you can answer this question, or at least have a sufficient condition, by looking at the differential of your dynamics with respect to x. So you're going to call this the matrix A. You're going to call the matrix B, that's the differential with your control. Now you're going to build a big matrix that is B, A times B, A squared times B, A cubed times B, and so on, up to A to the power n minus 1 times B. And if this big matrix has a rank equal to n, then the answer is yes. So you see, it becomes a little more complicated now. So it's a little more complicated, and so it's a perfect second task. Sorry? N is the number of rows. Yeah, so n is the same size as x. So it's a number of rows, so it means that your matrix can be very, very large, but it's not very tall, and the question is whether it has a max possible rank, which is just the number of rows, indeed. So indeed, that's a trap for a lot of master students who try to compute the entire matrix when usually you can only compute the first few columns, and then it's already rank n, and you can just stop here. So yeah, I still feel bad about the last exam I gave last year. Okay, so this looks like a perfect second task for our transformer. So can we answer this question with Kalman's theorem? Okay, so I can give again an example. The example is this one, for instance. So you see we have a control U. So I'm trying to see if I can make it. Yeah. So you have a control U here, and the question is, can I do whatever I want? It's the mathematical question, but it's basically saying, can I do whatever I want around 0 with this system if I can choose U as I want? And for this system, the answer is yes, but you need to pay attention and because if you change even a small thing in the system, the answer can quickly become no. So really, it's kind of a non-local property of the system. You can't just look at a small part of the system and answer. You really need to look at the full system to answer this question. All right, so we use a similar setup as before, and then we try to see what happens. And now, instead of giving you the results by number of equations, I give you the results by and looking at the different parameters of the model. So size of the model. So you see that at the end of the day, with a still relatively small model, dimension 512, 6 layers, you get 97.4% accuracy on this task, where we are still using a data set where the chance level is 50%. And even with very small model, you have a good accuracy. So why do I say that 80% is a good accuracy? Is that when I try this with master students, the accuracy is around at 70%. So I feel like, yeah, that's the course I teach. So I feel like it's a pretty good accuracy. So same thing, and here we don't yet have the problem that François was having with the backward generator, because if you have a random system and you can directly apply your theorem and get a solution, so you can generate your system at random in an IID fashion. You don't really need to go back to some weird distribution because you are doing a backward computation.
Nevertheless, the way you are producing random functions.
Okay, I'm going to come back to this at the end, but indeed. So we are producing both in the most IID form you can find, but you could say, what happens if I bias a lot my test distribution? Does it work as well? So that, we're going to answer this question on the last slide. So that's a very good question. All right, so let's complexify a little more, and I promise it's not the last system, but nearly. Let us increase the difficulty. So we have the same system. X dot is equal to f of x, and u. U is still a parameter. And now you assume that the answer to the previous question is yes, I can do whatever I want when I choose u. But this is that's a mathematical property. That doesn't tell you how to choose u. It just tells you yes, you can. That's that's usually the difference of philosophy between mathematicians and even sometimes physicists. I remember talking of this problem with some physicists who told me, do you think there is a solution to this? And I answered very happy after 2 weeks. I was a master student. Yes, there is one. And they asked me, which one? I say, hey, no, come on. So here the question is, can you find k such that if you choose u as k of x, k times x, so k is a matrix, can you find k such that all solutions tend to 0? So back to our first problem. Now you can choose k. So again, provided the initial condition is small enough. And so here again, you have a theorem that tells you that the answer is yes and gives an explicit k, which is not the nicest matrix you've probably ever seen because it looks a bit nasty, but it's a solution, and it's an explicit solution. So there is one. This is obtained, so it's a theorem obtained from the Gramian, that's why I give this name. So it seems more complicated this time, but yeah, let's try. So this is the third task. So can we find such K? And so, yeah, so once again, we know that there is at least one K, that maybe there are other solutions, and in fact there are probably infinitely many solutions, but at least we know that there is one, so we can ask this question, and there is one given by this formula. So if I take an example again, so this is our previous system, and what you would output this time is not a yes or no, but now you want to output a matrix, so it could be just a vector, it could be a full matrix, of float. So we had a debate before about whether it's hard or not to predict floats. Here it's just an ensemble of floats, and you need to have them in the right order. And for this example, you have here the matrix K, which is most probably false because I took the values at random. I planned on computing it during this morning's talk, but it was too interesting, so I couldn't. And I thought that it's not like you were going to compute this in a few seconds and tell me that I'm wrong, so I left it. All right, so as input, you will have a string of tokens. I'm just writing here, recalling what François said and showing what it will mean. This means that you will start to have some string of tokens that are larger than before, and this might matter because we have small models, so this just might matter. And for this reason, I thought really this is a hard problem, and there's no way the transformer will work this time. But I would have been wrong thinking this, because it still worked with a pretty decent accuracy. The line you would like to look at is correct feedback matrix, so it means, yes, it works. It found a correct K, a K that ensures that the solutions are going to 0. And you see that, so with the number of equations, you see that you can have, for instance, very high accuracy with 3 equations, and if you believe that 3 equations is simple because it's only 3 equations, just remember that this example is 2 equations. So you have a pretty high accuracy, but what's really interesting here is that if you try to wonder, okay, what is this K that the model is outputting? Does it look like the type of K I was giving in the training set? So if I compute this big matrix, does the solution of the transformer looks like this one? And the answer is nearly never. So for 3 equations, half of the time, but quickly it's nearly never. Like for 6 equations, it's 0.4% of the time. So yeah, let's say yeah, 1% of the time then. Somehow, yeah.
How do you know that the output is? You have to do a calculation.
Oh yeah. We have to, for the second line, we have to do a calculation. So we know so we have a system. We ask the transformer to guess. It gives an answer. We check that the answer is correct, and then you can actually just look. So it's. No, it's actually still a locally stable. So K is always given here, so that if you look at the linearized system, the eigenvalues will be strictly negative because it's just then instead of having A. So if you differentiate with A and B as before, you will have A plus BK, and you have a theorem that tells you that if AB is controllable, then you can always find a K that decreases as far as you want. So of course we don't say this to the model, but the model finds out something with a decay rate that is sufficiently far from 0 so that we don't have any problem. And then we can test whether it looks like the other one. So it really finds another type of solutions most of the time. And
Was there always a K? 50% of the time is it supposed to say there is no K?
No, here there's always a K. So yeah, so it, like for instance, the overall is 66.5. I mean, it should have been 100 if it was perfect. But still, we're trying to predict something that starts to be pretty complicated because it's not even one float, it's several floats, and at the end of the day, you would like them to be good enough so that your system converges to something correct.
Sets of K which work can be cubed, right?
Yeah, set of K. But yeah, it's.
Just ask you to produce random.
Oh, yeah, no. So we try with random matrix. So this works a little bit with one equation because with one equation, it's just half of them works. and then if you start with 2, it starts to be more complicated, and at 6, you have basically no chance of getting. But that's actually a very good question. The reason why it can find something else is just because there's a wide number of cases that will work. The question why the theory is outputting you this one is just because with this, I mean, when you're working with symbolic things, you end up with objects that might be hard to compute, but that are giving you the answer that you want. So that's basically the reason why. It's also linked to the optimal control, but I don't want to enter this detail.
Can you follow the feedback matrix?
Oh, feedback matrix is K.
Oh, it's
K is yeah, it's called the feedback matrix.
and
Then
the one computed is Gramian?
Gramian is, so, okay. Feedback matrix, it means it outputs a K that works. And what we call Gramian is the one given by the theory. It's this one. So what we're saying is that the K that the transformer is giving is most of the time not the K that you will compute here. No, it's not at all a unique solution. There are a lot of solutions, like infinitely many. And that's the one often used, that's the one you would find in textbooks. But there are infinitely many. I mean, it's easy to show. All right, so that's the end of of this part on the problems that we know, and we're just trying to see if we can kind of teach a theorem to a transformer. I'd like to do a few remarks. In all these problems, they have in common that there is no simple interpolation. That's the reason why we have the theorems. And still, after training on only a few million examples, so once again, a few million examples seems a lot, but it's very small compared to the vast majority of the space, it seems to generalize to the whole space. And to convince you about that, we tried to see whether the learning was robust or not. So we tried on bias distribution. So now you can extremely change your test set by saying, for instance, I'm just not going to use those operators, or I'm just going to use this thing, or much often this thing. And it essentially doesn't change the accuracy. You can try something that is riskier, is saying I'm going to try on longer sequences. So François told you that for graph, for instance, you will not be able to, I mean, you trained on graph from 0 to 100 nodes, you will not be able to find the solution for 200 nodes. Here, we're doing exactly this. We're saying, okay, we have a training set where the length of the functions are between 3 and 2n plus 3, where n is a given number. And we are testing on equations where the length is 2n plus 3 to 4n plus 3. So basically, there's nearly no overlap. So you're really testing on something you've never seen. And it seems to work. It slightly reduced the accuracy still, but it seems to work pretty well as well. And the one that really made me, I mean, yeah, the one that really surprised me is the last one. You know, it's this kind of situation where you're not a machine learnist, at least by training, you end up seeing the results and thinking it's black magic. I don't know if this ever happened to you. That was about the case in this one. We trained on 2 to 5 equations, and then we tested only on 6 equations. So the model has never seen a system with 6 equations before. It has never seen the variable x6 before either, but it still works with pretty decent accuracy. So that's all on this part. I'd just like to add that, you know, as François said, there are many other mathematical problems that can be tackled with this. So you can do pretty much many other things. And of course, all the code is open source if you ever want to try it. So I'm now going to talk about the second part with some examples of promising open problems. So what do I mean by this? So let's go back to our first stability problem. So you have dot x is equal to f of x. And you would like to know if all the solutions tend to 0 when t goes to plus infinity. So I told you that there is no satisfying way of answering this question. Well, indeed, but there is still something. It's called Lyapunov theory. It's an old tool. It dates from 1892, if I'm correct. That's the one example where the Lyapunov is basically more famous for what he did during his PhD than for what he did for the rest of his career. But yeah, there are opposite examples. So. This theory tells you that if there exists a Lyapunov function, so what's a Lyapunov function? Is a function v that satisfies those 3 things. So it's always positive and equal to 0 and 0. It tends to plus infinity when x goes to plus infinity. And most importantly, it satisfies this condition, this weird condition. It tells you that the gradient of v scalar, the dynamic, is strictly negative for any x. So if you can find such a v, then the answer is yes. Your system have all solutions that tend to 0 when t goes to plus infinity. So how does this work? How does this theorem work? Just to give you an idea. Well, if you take your Lyapunov function and you differentiate with time along the trajectory, so you take v of x of t, where x is a solution, and you differentiate, it will give you gradient of v times dx over dt, but dx over dt, it's just the dynamics, it's f of x. If you look back, it's dot x is equal to f of x. And this we asked with the third condition that it's always negative. So your Lyapunov function will be decreasing strictly over time, except when you are at x equals 0. And thanks to the two first conditions, you will manage to show that this indeed represents well enough the state of your solution, and you will manage to show that x goes to 0. So that's the way it works. And you kind of, I'm sure you've already seen this in a less abstract way before. If you look again at the pendulum, you know, if you have a pendulum and you put it away from its equilibrium position, it will go back to 0. And the way you will show this will be by saying, no, I know that there is something called mechanical energy, and since there is friction, mechanical energy is strictly decreasing with time except when the speed is equal to 0, so when I'm down. This is exactly what we're doing here. So this, in some sense, Lyapunov functions are a generalized version of the energy of the system. It's a quantity that is hidden somewhere in the system that you would like to find. So if I'm giving an example, this is an example of system. So this is pretty much very basic system where you will ask yourself, do all solutions of the system on your left tend to 0 when t goes to plus infinity? I would lie if I told you that I think this is obvious to answer yes, but if you know the Lyapunov function that is on the right, the answer becomes much easier. And finding this Lyapunov function is quite hard. I mean, guessing this, you might think that because there's x5, x15, maybe x16, but guessing this is pretty hard. But once you have this, checking it is easy. So we can do it together. Obviously, if x1, x2 goes to plus infinity, then, I mean, if the modulus goes to plus infinity, then your function will go to plus infinity. It will be always positive, except if x1 equals x2 equals 0. And for the most important condition, just this, you can just compute. The gradient of v is 6 times x1 to the power 5 and 6 times x2. You can do the scalar product, and after a few computations very quick, you end up with minus 18x1 to the power 8 plus 12x2 to the power 4. This is strictly negative, so you're done. So yeah, it needs to be strictly negative, except when x is equal to 0. That's something I forgot to write. So as you see, checking that it's a Lyapunov function is pretty easy. Guessing the Lyapunov functions is harder. And so you might say, okay, maybe I have a chance to guess this Lyapunov function with this system. You just give me 10 minutes. So if you tell me this, I will give you this system, which is still not that complicated. It's only 3 equations. It's polynomial. But then it's going to be hard to say that the answer is yes, except if you know the Lyapunov function that I've written on the right. So yeah, so that's not an easy task. So Lyapunov theory is a very powerful theorem in principle, because nothing tells you how to find a Lyapunov function. And so the open problem behind that has been around for more than 100 years now is, given a stable system F, can you find, and which one, an explicit Lyapunov function V? Explicit is important here. It's not about proving that there exists a Lyapunov function. Really, the question is, you want the Lyapunov function. So it's a bit hard because I've heard several times that it's apparently an NP hard problem, so I haven't checked, but I've read that in several papers. So yeah, that's kind of a problem. But maybe there is a class of system, a large class of system for which it's not the case, and if you remove some few pathological cases, it could still be solved, but we have no way of finding Lyapunov function yet.
NP hard is the size of X goes to infinity.
Sorry? Yeah.
NP hard, what's the input?
Oh, it's just...
X is n-dimensional.
Yeah, X is n-dimensional.
So as n goes to infinity.
As n goes to infinity, I have no doubt, but I thought that even if you have n fixed, you could have something very hard. So I'm not sure. I'm not sure at all of that. I've literally checked on the paper before the talk, so I wouldn't bet anything on this. Just to say that could be hard. So here anyway, we're going to stop at n equal to, I mean, even 10 will be nice.
Given a stable system, do you know by theory that the Lyapunov function exists?
Okay, so that's another complicated question, but in most systems, yes. But we're cheating when we're saying this, because when we say yes, you can always reconstruct a Lyapunov function from the trajectories. But it's not explicit at all, because it supposes that you know the trajectories. So if...
I mean, at least you know that the answer is that a Lyapunov function exists. Otherwise, you are...
No, completely. But no, the big problem here is that even if you know that it exists for a stable system, how do you find a global stable system?
I think the question is, given a stable system,
Yeah.
there definitely exists a Lyapunov function.
So, okay, I don't want to say any bad things here, but I really think the answer is yes. So I think we had to check this. So I get the question, and the answer is yes. The main problem is that even if this is true, giving the input is already hard. Like identifying a stable system if you don't know the Lyapunov function is hard, because it's the only way we know for most of cases. All right, so we can try to do this. So you see me, I guess you see what I like to do. It's very hard to guess, but it's very easy to check. So I could ask the machine to guess, and maybe I can check it. But then there are at least two main challenges. The first one is, how do you generate enough training examples for a problem we don't know how to solve? And that's a big problem, right? Yeah? Yes?
You could generate the Lyapunov function, and take the gradient and perturb.
Exactly. That's my next that's my next slide. So previously we were sampling at random and using the theorem to generate a solution. So I thank you a lot for following as well. That's very appreciable. It's not possible anymore, so we will do, like François was presenting, a backward approach. Instead of finding the solution from the problem, we find the problem from the solution. So if you can find, and that's not very easy, that's not very hard, sorry, a mathematical way to get, where from a Lyapunov function that you will sample at random, you will find all possible systems with this Lyapunov function, so you can sample in those systems, then you can just sample the first one, sample the second one, and that will give you a data set. And in spirit, the key tool when you're doing this, mathematicians always like to try to see what you're really leveraging when you're doing something. So here, what you're really leveraging is that checking the solution is easy. So finding a system for which the Lyapunov function, so from a Lyapunov function, finding a system is easy, but the other way around is very hard. So there are limitations, of course, because even if you can, in principle, generate all possible stable systems, you are generating backwards. So remember what we said. We are generating a very few number of examples compared to the whole space. So if you have a bias distribution and you generate a very few number of examples, well, you're just going to generate examples everywhere at the same place. So the question is, can you do this in a way such that you can still learn on the whole on the whole space? And that's what brings to the second question: how do you get a reliable test set? Again, for a problem where I can probably find you 2-3 systems for a test set, maybe 50. If you have a way, so I'm asking to the potential mathematicians here, if you have a way to give me 10,000 stable system not going through this procedure, I'm listening. And I would be very happy. The first thing I can say is that, and the first thing we tried so far is just making sure that you can't find, so once you train your model, the thing that you don't want is learning the generator or not learning the problem. So the thing you could try to do, at least as a safeguard, is trying to guess the solution with not enough information. So you hide part of the information, too much to find the solution, and you see whether the transformer still managed to. If it does, then you're in trouble. So this is still a work in progress. That's why I don't have the answer to this question. So I didn't plan to show any result, but I thought it will be maybe a bit frustrating. So I can show you something where we don't know yet whether it's very valid or not, just saying that it seems that it's trying to learn when you try on polynomial. So it's a simpler case. It's a polynomial systems with polynomial Lyapunov functions, for which we can try to do many things in theory. And so you can actually see that it seems to learn something. Sorry? Integer coefficients, yeah. Yeah, no, otherwise it starts to be, again more complicated, yeah. Integer coefficients and integer between, quite high sometimes, though.
You want polynomial Lyapunov functions because it's easy to ensure that they are positive? Because you put squares.
Yeah, so you want this because you have actually a few results on this, even there are not many, and so you would like to compare with the existing results where you can say something. It's always in the question back to how to get a reliable test set. Maybe for those type of examples we can. It's not as interesting because there are methods or routines or algorithms to try to guess something in here. But the thing is, we believe that if this procedure works for polynomial systems with polynomial Lyapunov function that are in fact in sum of squares, maybe we can do something more general. So I have only 2 slides left, so I guess that's we'll be on time. Another open problem that will be interesting is to identify integrable systems. So what's an integrable system? It's a special class of differential equations that are so symmetrical that at the end of the day they allow to find explicit solutions. I think that's the easiest way to explain it, especially in one slide. And they can be identified by something called a lax pair. And so the problem is that checking that something is a lax pair is easy, but finding a lax pair is very hard. So you see where I'm going again. We could try to use the exact same thing with this, and this is current work with François Charton, Harini Desir-Rajou, and Alexandre Krajenbrink, who are here in the room. So if you have questions, you can ask them directly. And I think this is it. So when I was a PhD student, I always heard that the last talk of a conference should have 4 main qualities. It should be light, concise, brief, and short. So I don't know for the light part, but I tried to be concise, and at least I hope this was fine. Thanks a lot.
Yeah, we're going to take questions from the audience, and I guess if you have questions about the previous talk too.
François, can you come back?
Yeah.
Thanks a lot. It was a pair of great talks. I was wondering, across a lot of these examples, it seems like you get super high accuracy on all of these. Is there anything informative about the small number of cases that you get wrong in these examples?
That's for you.
So, yeah, that's a very good point. So there's a couple, can you hear me?
I don't think it's on.
Yeah, this should work. So the point is that when you are 99% accuracy, you usually cannot say anything. Because you always have a few cases where usually the syntax is perfect, but sometimes it's not. And it's half of a percent, that's a tenth of a percent. So when you're around 99.9, that's the reason why I chose, the eigenvalue and inversion problem to do failure cases. Because you could always have a half-trained model, but then if the model is half-trained, what do you learn, actually? And if the trained model is 99%, what can you do on a failure case? So you could always augment, I think, the size of the test set, but not much more. The experiments on failure case, we started, they're all actually a month old, and we never tried on previous examples, but it would definitely be something interesting.
Yeah, what got me expected, though, is that in the very pathological cases, like the one where, I don't know, you can show, so I haven't talked about this here, but you can show that for some systems, for instance, for the Lyapunov functions, for a given system, it works, and if you change by any arbitrary small epsilon, it just doesn't work anymore, because the coefficients were rational, and then suddenly you have something that is not completely rational at the same place and doesn't work anymore. For those cases, it will be very surprising that it works, given that you're outputting something that is by nature approximate, even if it's very precise. But, you never know.
I have a question regarding the linear algebra part. So there are some open problems in linear algebra, and I was wondering if this could be applicable to try that out with neural networks. Like, for example, with eigenvalues, there is the non-negative inverse eigenvalue problem. Like, given a set of numbers, are they an eigenvalues of a non-negative matrix? So it seems like, you could train a model to basically kind of predict a matrix from a list of eigenvalues and see.
Yeah, this is definitely a great idea. Because this is the kind of thing when, it's very easy to train and test that, because basically you generate the backward thing,
Yeah.
and then there you go. So it's easy to generate and very hard to guess. So yeah, thank you for that. I'm actually quite interested in that.
Okay.
But yeah, there are problems like that. The direction we were looking at, to try to do generalization would be graphs, because graphs, you have many cases, and sometimes it's even provable that you have cases which are very difficult and cases that are easy, and they're very close. Mm-hmm. Because we know generalization is a local property. You need to not be too far. So you want the hard case to be close in some respect to the difficult case, and yeah, graph might be like that. But yeah.
Thanks.
Hello, thank you both for your talks. I had a question again for linear algebra examples. Some of these problems, like taking the SVD of a matrix, they have a particular complexity assigned to them. For example, we can SVD in cubic time as a function of the dimension, blah, blah, blah. But there are some weird results, like if it's not over reals, if it's on booleans, then it becomes hard, like there's a switch. I think that's right. But in general, many problems in linear algebra, if you change the field, it becomes hard. And some problems are hard already. For example, determinant is easy, permanent is hard. I was wondering if you get the transformer struggling in the hard cases? Like, can it see the complexity? Stuff like that.
Yeah, it's interesting. There are a couple of cases where the problems are hard and we know why. For instance, someone talked about the parity yesterday, and there's a published paper a couple of years ago, Shaef Schwartz and other guys, who showed that parity integration is hard, basically because the gradient is uninformative. Because when you have two values, characteristic 2, it can go either way. So the gradient doesn't tell you anything. So there's no way you will ever learn from the gradient. So there are specific cases which are hard, you know why. As for whether the cases, the difficult cases are easy, I think Amaury's presentation shows that it doesn't follow the same logic, or not always. Because for the matrix, sort of. But you see, the controllability should be much harder than the rest, and it's not.
Okay, thank you. So let me just make a comment before, and then we can pass to another. Sorry. So the parity thing, learning the parity language, it's hard because of our bad encoding. If you linearize the problem, if you make it learn a matrix, a linear matrix, to learn the XOR linear map, you can do this, right? I imagine you can train it, it becomes smooth, you can do it. So it's because bad encoding, right? But some problems we just believe to just be hard. There's no way around them, like permanent, or I don't know what. Some stuff in knot theory, like Jones polynomials, or partition functions. Some stuff is just hard. SAT, I was wondering if these AIs can really see these hardness transitions by how much they're struggling to find the answer, or if you can see these from explainability metrics that you check.
So I have not really an answer to this question, but it's something that is, if you remember it's a very partial answer. If you remember the curve, the accuracy curve that François showed, they were like doing some weird stuff. This is something that we observed on like all of these examples, nearly, except for the very last one I showed you. So it gains 20% and seems to give 20% again. And I think it was a very nice example when you show that actually at some point you have the sign and then the absolute. But that's a very partial answer, and I leave you.
That's how it should show up in general.
Even though sometimes, on integer problem, I did a lot of modular arithmetic for the crypto problem, and you get, Christine showed some of those curves with, steps yesterday, and, in the beginning you say, oh, it's learning the first bit or the second bit, and that's so easy. And actually, no. Actually, no, when you try to see what is learned at that time, it's very tough to understand. So you have steps, but you cannot always explicit, or maybe I'm not creative enough, but it's not always easy to understand what the steps are made of.
Thanks very much for your talks. I had a question, François, for you about this embedding this projection of the Latin space of the transformer. So in physics, there are many universality results. For instance, the spacing of non-trivial zeros of the zeta function behave as like the spacing of eigenvalues of a random matrix. Could you see this kind of universality or analogies in the Latin space of transformer?
So I haven't looked, and I would sort of dot it. The problem with interpretability by looking at the attention heads or looking at the embedding is that it provides very nice figures, and this definitely helps you get reviewed and get accepted in papers because it's nice and people like it. But you usually can say very little thing. I spotted the squares, but what does it mean? I don't know. The main problem you have with the embedding is that the embedding is in a very high dimensional space. And the only thing I can show is like a 2-dimension projection. And okay, you have large eigenvalues for the two largest dimensions, but usually there is very little to tell. The only thing you can see is that there is some kind of order, and so clearly something orderly is being learned. But this is unsurprising, and this is the whole point of learning. So I would tend to say that I very much doubt, I know some people try to do that there's a real possibility to do good explainability just by gutting the transformer and trying to understand. I think what I've tried to do in linear algebra, which is designing special cases with special test sets and trying to leverage theory is a much better approach.
Thank you for your nice talk. I'm wondering that the assumption of the training of the transformer was that the component of the matrix are independent. But finally, we have a good accuracy in generating. But do we still have those independency between components? I mean, the distribution could be nicely same or as we want, but the independency between the component, is it still there or not?
Not sure. I didn't really heard the question. Sorry.
I'm not sure I really understood the question. Can you say it again?
Loudly. Okay. And one of the assumptions was that the independency between the component of the matrix is exist, and then we train a transformer. Yeah. Then we can generate, right? And the generated matrix have those independency still or not? I mean, the nice distribution is there, but is the independency also is there or not?
So the thing is that when you train matrices, when you generate the matrices, you basically generate, the simplest way to generate them is generate all coefficient independence. If you generate this way, this will be all through your test sets. If you want to change that to non-independence, it's difficult because what's non-independence? So the trick we use to generate that is that you generate a matrix with independence, and then you perform a diagonalization or an SVD on it. So you have an orthogonal matrix and you have a diagonal, and then you remove the diagonal and change it, and then you remultiply, and then your matrix is, for theory, it's no longer independent. You don't know how to generate it, but so you use a trick to generate a matrix like that. So that's the way you do it. And actually, it was made possible because the trick exists. You see, that when I say leveraging theory, it's stuff like that. It's you can use some theory you have in linear algebra or in math to sort of doctor the way you generate the generator, the way you test what you test on, and the properties you expect from the generator and the test set.
Thank you for the interesting talks. I just have a question regarding the first presentation. I think it was in the second problem. Do you have an idea why the accuracy dropped for the large models? I think there was
Yeah, I do. Definitely. I didn't gloss a lot over that. I actually had an XXL size that never worked, that I never added. The problem with transformers is that the transformer we use have that thing called quadratic attention. So basically, the complexity, the speed, and the memory usage is quadratic in the length of the sequence. So when you have graphs with many nodes and 3 times as more edges than nodes on average, you end up having very, very long sequence, like 1,000 or 2,000. And basically, after 1,000 token up to 2,000, it becomes very, very slow to train, and sometimes it's much tougher to train. So I think the main reason why the results were lower there is that I sort of lost patience at some point, and trained for a week, and I said, okay, that's enough. I would expect it would work, but in general, you have that trade-off. If you have very long sequences, sometimes you end up not being able to train. So there are alternatives to that, but it implies, using sparse attention, so simplifying the attention model, so you're going to lose some signal in it. And I still want to train that because it's unclear that if you remove some signal, whether you can still learn the problem or whether you're going to lose, the efficiency. So there's a trade-off there. And this is really a problem right now with transformer, which is the length of the sequence.
Okay, thank you. And what happens then if you train the smallest one for the same number of epochs, like when you stop the largest one? Do they still have better performances or the same?
So, yeah, that's a good question. So this is called retraining. Basically, you train on one size and retrain on a second size. So I don't have experiments on graphs, but I experiment a lot on matrices for that. And what I see is that, for instance, if I'm learning 5 by 5 matrices, and then I stop learning it and start learning 6 by 6. So 6 by 6 is not learned, but I start working on 6 by 6. I need less examples to retrain. Less examples is like twice less. So it's not just a few. It's not few-shot learning, as they call it. I still need millions of examples, but I need less. Another observation I have is that if I'm training 8 by 8 matrices, with the transformer I have 8 by 8 is pretty much the largest I can do on Wigner matrices. 10 by 10 I cannot train, at least not on 360 million examples or something like that. It really doesn't work. But the funny thing is that if I start training on a mixture of 5 by 5 to 20 by 20, all the dimensions are learned. So if you have diversity in your training set, it will take a lot of examples, really, weeks of training. But if you have diversity in your training set, you might be able to scale up better. All of this is in the paper on matrices. So when you retrain on something you have never seen, what you're going to have is that you will need less example. Another thing you will notice is something called catastrophic forgetting. Basically, you will learn the first problem to learn the second. So if you want to, you need to retrain on the 2 dimensions. And then if you have a diversity of dimensions, then it somehow learns better than if you have only 1 dimension. Those are, experiments on eigenvalues.
Okay, thank you very much.
I have a bit more curiosity rather than a question. From all of the from the 2 conversations that you had, it looks like that you are basically able to master like linear algebra and like calculus in some sense. Would it be possible to try like some form of like financial mathematics where you add like the complexity of the stochastic calculus? Is it feasible to do that?
So we have 1 experiment with stochastic data. So it depends, because if the noise, so transformers tend to be resistant to noise, so long the noise is not too big. When the noise becomes big, you have a problem. So if by stochastic you want to work on time series, a time series, the thing is that you have a very simple model, basically linear with a few things, because you have a lot of noise and you want to eliminate the noise, and with a lot of noise, in presence of large noise, there's nothing you can learn except small models. And so I would expect transformer to be less efficient in that case than time series methods. Now, we have an experiment we have done during the symbolic regression paper where we try to add, among our functions, there was 1 new function which was called random. And this function was producing a random number with a specific distribution, Gaussian or something like that. And the funny thing is that the model could be trained to identify where the randomness was in the formula. So it could identify a formula with a random coefficient, saying, for instance, this is x squared plus u, or plus u squared, or plus cos u, where u was random. And it would get the right formula. So yes, it's possible to learn stuff about stochastic data. It hasn't been studied a lot, so it's really future work or something. Someone is interested. It's really something that should be done.
There's also an answer that is each time we say, oh, there's this super new problem. It's exciting and so on. It's going to be done in a week, and then you're still here 7 months later.
Also, I know I asked someone who knows people in finance and quants. And I've been told that, obviously quants have tried to use transformers, and there probably are transformers running. It's not typically the kind of thing that people make public, but they probably use transformers or models like that for some prediction in finance. I just don't know of it because it's typically unpublished.
All right, if there are no more questions, let's thank the speakers again. I just want to say a couple words